grounding bank is a three-phase transformer bank connected in a Wye-Delta configuration. It is used to establish a neutral point on a high-voltage electrical system. The grounding bank consists of three single-phase transformers connected in a Y configuration on the high-voltage side and a delta configuration on the low-voltage side. The high-voltage windings of the transformers are connected to each other at a common point, creating a neutral point. The low-voltage windings are connected to each other to form a closed loop. This is the delta connection. The neutral point of the Y-connected high-voltage windings is grounded through a grounding resistor. The grounding resistor limits the flow of fault current through the neutral point and prevents excessive voltages from developing on the system. The connection of the neutral point to ground creates a low impedance path for fault currents. When a fault occurs on the system, current flows through the grounding resistor and into the ground, isolating the faulted section. The grounded neutral also provides a reference point for voltage regulation and harmonic filtering equipment. The neutral point of the grounding bank can be extended to distant locations through distribution lines or substations. The extended neutral line provides a common reference point for voltage and current measurements, allowing for proper grounding and protection of equipment. Firstly, grounding banks establish a neutral point for grounding purposes. Secondly, they limit fault currents and prevent overvoltages. Thirdly, they provide a reference point for voltage regulation and harmonic filtering. And fourthly, they improve system stability and reliability. The Wye-Delta configuration of the grounding bank plays a crucial role in creating a stable and reliable neutral point for high-voltage electrical systems. Let's delve a bit deeper into the purpose of each connection, starting with the Y. The Y connection, also known as a star connection, is characterized by having one end of each of the three windings connected to a common neutral point. This neutral point serves as the reference for the system voltage and is typically grounded, either directly or through impedance. The primary purpose of the Y connection in a grounding bank is to provide a stable and well-defined neutral point. This neutral point is essential for several reasons. 1. It allows for the detection of ground faults. When a ground fault occurs, a current will flow from the faulted phase to ground, and this current can be detected by monitoring the current in the neutral connection. 2. It limits overvoltages during ground faults. By grounding the neutral, the voltage on the unfaulted phases is limited, preventing them from rising to dangerous levels. 3. It provides a path for zero-sequence currents. Zero-sequence currents are currents that flow in the neutral conductor and are caused by unbalanced loads or faults. The grounded neutral provides a low impedance path for these currents, preventing them from causing voltage distortions. Now let's examine the delta connection. The delta connection is characterized by having each of the three windings connected in a closed loop, forming a triangle. There is no neutral point in a delta connection. The primary purpose of the delta connection in a grounding bank is to provide a path for circulating currents. These circulating currents are caused by slight imbalances in the transformer windings or in the system voltage. The delta connection allows these currents to flow freely, preventing them from causing voltage distortions or overheating. The delta connection also helps to suppress harmonic currents. Harmonic currents are currents with frequencies that are multiples of the fundamental frequency, such as the third, fifth, and seventh harmonics. These currents can cause a variety of problems, including overheating, voltage distortion, and interference with other equipment. The delta connection provides a low impedance path for harmonic currents, helping to reduce their amplitude. In summary, the Y connection provides a stable neutral point for grounding and fault detection, while the delta connection provides a path for circulating currents and helps to suppress harmonic currents. Together, these two connections work to create a grounding bank that provides a stable and reliable neutral point for high-voltage electrical systems. Now consider the grounding resistor. It plays a crucial role in limiting fault currents and preventing overvoltages. Without the grounding resistor, the fault current during a ground fault could be very high, potentially damaging equipment and causing a safety hazard. The grounding resistor limits the fault current to a safe level, protecting equipment and personnel. The value of the grounding resistor is carefully chosen to balance the need to limit fault current with the need to provide adequate sensitivity for ground fault detection. A higher resistance will limit the fault current more effectively, but it will also reduce the sensitivity of ground fault detection. A lower resistance will provide better sensitivity for ground fault detection, but it will also allow a higher fault current to flow. In general, the value of the grounding resistor is chosen to limit the fault current to a level that is below the interrupting rating of the circuit breakers in the system. The location of the grounding bank is also an important consideration. Grounding banks are typically located near the source of power, such as at a substation or generating plant. This minimizes the impedance between the grounding bank and the source of power, which helps to ensure that the grounding bank is effective in limiting fault currents and preventing overvoltages. Grounding banks can also be located at other points in the system, such as at the end of a long transmission line. This can help to improve the grounding performance of the system and reduce the risk of overvoltages. The neutral point that is established by the grounding bank can be extended to distant locations through distribution lines or substations. This extended neutral line provides a common reference point for voltage and current measurements, allowing for proper grounding and protection of equipment. The extended neutral line is typically grounded at multiple points along its length to ensure that it remains at a stable potential. The grounding of the extended neutral line is typically done through grounding rods or other grounding electrodes. The number and spacing of the grounding electrodes will depend on the cell resistivity and the desired grounding performance. The extended neutral line can also be used to provide a return path for neutral currents. This can be particularly useful in systems with imbalanced loads where the neutral current can be significant. The extended neutral line must be sized appropriately to carry the expected neutral current. The grounding bank plays an important role in protecting equipment from damage due to overvoltages. Overvoltages can occur due to a variety of factors, including lightning strikes, switching surges, and faults. The grounding bank helps to limit the magnitude of overvoltages by providing a low impedance path to ground. This helps to protect equipment from insulation breakdown and other types of damage. The grounding bank also helps to improve system stability and reliability. By providing a stable neutral point, the grounding bank helps to reduce voltage imbalance and improve the performance of protective relays. This can help to prevent cascading failures and improve the overall reliability of the system. In addition to the benefits mentioned above, grounding banks can also help to improve power quality. By reducing voltage distortion and harmonic currents, grounding banks can help to improve the performance of sensitive electronic equipment. This can be particularly important in industrial facilities and other locations where power quality is critical. Grounding banks are an essential component of modern electrical power systems. They provide a variety of benefits, including improved safety, reliability, and power quality. The Wye-Delta configuration of the grounding bank is carefully designed to provide a stable neutral point for grounding and fault detection, while also providing a path for circulating currents and helping to suppress harmonic currents. The grounding resistor plays a crucial role in limiting fault currents and preventing overvoltages. And the extended neutral line provides a common reference point for voltage and current measurements, allowing for proper grounding and protection of equipment. Now let's consider some specific examples of how grounding banks are used in practice. In a typical industrial facility, a grounding bank might be used to ground the neutral of the main service transformer. This would provide a stable neutral point for the entire facility, helping to protect equipment from damage due to overvoltages and improve power quality. In a wind farm, a grounding bank might be used to ground the neutral of the wind turbine generators. This would help to protect the generators from damage due to lightning strikes and improve the overall reliability of the wind farm. In a data center, a grounding bank might be used to ground the neutral of the uninterruptible power supply (UPS) system. This would help to protect the sensitive electronic equipment in the data center from damage due to power outages and voltage fluctuations. In a hospital, a grounding bank might be used to ground the neutral of the emergency power system. This would help to ensure that critical medical equipment continues to operate during a power outage. Grounding banks are also used in a variety of other applications, including in transmission and distribution systems, in commercial buildings, and in residential areas. In each application, the grounding bank is carefully designed to meet the specific needs of the system. Selection of the appropriate grounding bank for a given application depends on a number of factors, including the system voltage, the fault current level, the grounding requirements, and the environmental conditions. It is important to consult with a qualified electrical engineer to ensure that the grounding bank is properly selected and installed. The grounding bank is typically installed in a location where it is easily accessible for maintenance and inspection. The grounding bank should also be protected from the elements to prevent corrosion and other damage. The grounding bank should be inspected regularly to ensure that it is operating properly. The grounding resistor should be checked to ensure that it is within its specified resistance range. The connections should be checked to ensure that they are tight and free of corrosion. Any damaged or worn parts should be replaced promptly. Grounding banks are an important part of modern electrical power systems, and they should be properly maintained to ensure that they continue to provide reliable grounding protection. The Wye-Delta configuration, grounding resistor, and extended neutral line all work together to provide a stable neutral point, limit fault currents, and protect equipment from damage. By understanding how grounding banks work, you can help to ensure that your electrical system is properly grounded and protected. Understanding the impedance plays a key role for the current flow in these systems. Impedance is the total opposition that the circuit presents to alternating current. It includes both resistance, which opposes current flow, and reactance, which opposes changes in current or voltage due to capacitance and inductance. In the context of grounding banks, impedance is crucial in limiting fault currents and controlling voltage during ground faults. Firstly, the grounding resistor, as mentioned earlier, is a key impedance element. Its resistance value is carefully chosen to limit the ground fault current to a safe and manageable level. This prevents excessive current from flowing through the grounding system, which could damage equipment or pose safety hazards. Secondly, the impedance of the transformer windings themselves plays a role. The Y and delta connections have different impedance characteristics. The Y connection, with its neutral point, provides a path for zero-sequence currents, which are currents that flow during ground faults. The impedance of the Y winding influences the magnitude of these currents. Thirdly, the grounding electrode impedance is the impedance of the connection to earth. This includes the resistance of the grounding electrode itself and the resistance of the surrounding soil. A low grounding electrode impedance is desirable to provide a good path for fault currents to dissipate into the earth. In addition to these specific impedance elements, the overall impedance of the electrical system also affects the performance of the grounding bank. A system with high impedance will tend to have lower fault currents, while a system with low impedance will have higher fault currents. The grounding bank must be designed to take into account the impedance of the overall system. In summary, impedance is a critical factor in the design and operation of grounding banks. By carefully controlling the impedance of the grounding resistor, the transformer windings, the grounding electrode, and the overall system, it is possible to limit fault currents, control voltage during ground faults, and protect equipment and personnel. When a fault occurs on an electrical system, the grounding bank provides a path for the fault current to flow back to the source. The fault current is the current that flows through the faulted phase in the grounding system. The grounding bank limits the magnitude of the fault current to a safe level. This prevents excessive current from flowing through the electrical system, which could damage equipment or pose safety hazards. The grounding bank also provides a reference point for voltage regulation and harmonic filtering equipment. The grounded neutral provides a stable voltage reference, which is essential for the proper operation of voltage regulation and harmonic filtering equipment. Voltage regulation equipment is used to maintain a constant voltage level on the electrical system. Harmonic filtering equipment is used to reduce the amplitude of harmonic currents, which can cause a variety of problems. The grounding bank also improves system stability and reliability. The grounded neutral helps to reduce voltage imbalance and improve the performance of protective relays. This can help to prevent cascading failures and improve the overall reliability of the system. Cascade failures can propagate throughout the entire system, causing widespread outages and equipment damage. A grounding bank helps to prevent cascading failures by providing a stable neutral point and limiting fault currents. These features help to isolate faults quickly and prevent them from spreading to other parts of the system. In addition to improving system stability and reliability, grounding banks can also help to improve power quality. By reducing voltage distortion and harmonic currents, grounding banks can help to improve the performance of sensitive electronic equipment. This can be particularly important in industrial facilities and other locations where power quality is critical. For instance, a manufacturing plant that relies on automated machinery might be very sensitive to power quality disturbances. A grounding bank can help to ensure that the voltage and current waveforms are clean and stable, which can improve the performance and reliability of the machinery. The grounding bank is a critical component of any electrical power system. It provides a variety of benefits, including improved safety, reliability, and power quality. By understanding how grounding banks work, you can help to ensure that your electrical system is properly grounded and protected. The Wye-Delta configuration, grounding resistor, and extended neutral line all work together to provide a stable neutral point, limit fault currents, and protect equipment from damage. In addition to the technical aspects of grounding banks, it is also important to consider the safety aspects. Grounding banks are designed to protect people from electrical shock. When a fault occurs on an electrical system, the grounding bank provides a path for the fault current to flow back to the source. This helps to prevent people from coming into contact with energized equipment. The grounding bank also helps to limit the voltage in the electrical system during a fault. This reduces the risk of electrical shock. It is important to ensure that grounding banks are properly installed and maintained to ensure that they provide adequate safety protection. Grounding banks should be inspected regularly to ensure that they are in good working order. Any damage to a worn part should be replaced promptly. The grounding system should also be tested periodically to ensure that it is functioning properly. Regular testing can help to identify potential problems before they become serious safety hazards. In addition to the safety benefits, grounding banks can also provide economic benefits. By protecting equipment from damage, grounding banks can help to reduce downtime and repair costs. Grounding banks can also help to improve the efficiency of electrical systems. By reducing voltage distortion and harmonic currents, grounding banks can help to improve the performance of electrical equipment. This can lead to lower energy consumption and reduced operating costs. The initial cost of installing a grounding bank can be offset by the long-term savings that it provides. Grounding banks are a worthwhile investment for any organization that relies on electrical power. They provide a variety of benefits, including improved safety, reliability, power quality, and economic performance. By understanding how grounding banks work, you can make informed decisions about whether to install a grounding bank in your facility. The Wye-Delta configuration, grounding resistor, and extended neutral line all work together to provide a stable neutral point, limit fault currents, and protect equipment from damage. It is important to consult with a qualified electrical engineer to ensure that the grounding bank is properly selected, installed, and maintained.